This is our part 2, where we've looked at effect measure modification in greater detail. Now we're going to talk about interaction analysis. Our learning objectives are to differentiate between statistical and biological interaction, to learn how to assess and report, in particular, additive and multiplicative interaction. So to just give a brief definition, um, statistical interaction is when you have A and B, where we have two exposures, we can consider them statistically independent if the risk of the disease given exposure A and B can be adequately modeled as a function of separate effects of being exposed to A or being exposed to B. On the other hand, if an additional parameter is required to describe the risk of joint exposure, we say there is statistical interaction. So you have exposure A, exposure B. If they are coming together to give rise to our outcome of interest, we say that there is statistical interaction. We'll look at this in a greater detail. Biological interaction, where sometimes it is called interdependence, is the operation of two or more biological causes of a disease. So two factors will be considered biologically independent if the qualitative nature of the action of each exposure is not affected by the presence or absence of the other. If one is dependent, interdependent on the other, we would say that there is biological interaction. Interaction is also scale dependent, the same way that we have looked at in effect measure modification. As you recall, in effect measure modification, we had additive as well as multiplicative interaction, effect measure modification. We have the same thing here. We have additive interaction and multiplicative interaction. And sometimes we can have both. How do we assess interaction? For the sake of simplicity, we can assume that we have a binary exposure where we're calling it as G to denote a genetic factor of interest. We have our E, which is an environmental factor of interest, and we have D, which is our outcome of interest. For simplicity, we're assuming that all of them, the genetic risk factor, the environmental risk factor, and the outcome of interest, the disease, are all binary, which means 1 is present, 0 is absent. Suppose that we have the following data on a risk of a disease from a cohort study. We have our genetic risk factor denoted as G0 as absent, G is equal to 1 as present, and the environmental risk factor denoted as E is equal to 0 and E is equal to 1. So we have those 4 cells, classic 2x2 table in epidemiologic studies. The probability of the outcome, or the probability of the outcome in the presence of both the environmental risk factor and the genetic risk factor, is indicated here. P11 would be the probability of having the disease given the genetic risk factor and given the environmental risk factor. The probability of having the disease in the absence of both the genetic and the environmental risk factor is denoted as P sub 00, where probability of the disease given absence of genetic risk factor and environmental risk factor. And then we have the probability of having a disease in the presence of either of the risk factors. In the presence of a genetic risk factor, P1 sub 0. In the presence of an environmental risk factor, P sub 01. So we can evaluate the presence of our risk interaction, the effect of one exposure, if it's added to the effect of the second exposure using an additive scale or using a multiplicative scale. Let's look at how we measure or assess the measure of interaction on the additive scale. What we are saying is the measure of interaction on the additive scale is nothing but we're saying the risk of a disease in the absence of both exposures is P sub 00. The presence of a risk in the presence of both is P11. So what we are saying is if we subtract the underlying risk, where we're subtracting the risk in the presence of both exposures, P11 minus the underlying risk, subtracting that from the presence of an association in the presence of the individual risk factor, that is in the presence of an environmental risk factor only, which is P01, or the presence of a disease or an outcome only when the genetic risk factor is present, P10. So we're subtracting P11 minus P00, P10 minus P00, P01 minus P00. All we're doing is we're subtracting each from the underlying risk. So this gives us the measure of interaction on the additive scale. So what we are saying is conceptually the joint effect, where the presence of both exposures is that bigger than the presence of the individual effects. So we are subtracting the individual effects from the presence of both effects presenting together. Sometimes we use the terminology called RERI, which means the effect or the risk ratio due to interaction. So we can say that P11 minus P00 is the risk difference for the presence of both, and then the others are the risk difference for the presence of either of the risk factors. When we simplify this, we get this nice formula where we're taking the risk difference when both exposures are jointly present minus when the risk is for either exposure, the risk ratio for each exposure. So we call this the relative excess risk due to interaction. When both exposures are present, is there a more pronounced effect compared to the individual risk factors present? This is how we assess additive interaction. So if the value is greater than 0, if this number is greater than 0, we would say there is positive additive interaction. If the value is 0, we would say there is no additive interaction. If the value is less than 0, we would say negative additive interaction. Let's look at this in a simple example where suppose we have this data on a risk of a disease from a cohort study formatted in a similar way as the prior slide, where we have the genetic risk factor depicted as a binary variable 0 and 1, and the environmental risk factor as 0 and 1, and the probability of the disease presented in each cell. So what kind of interaction do we have? We can use the P11, subtract it from the underlying risk to understand the joint effect, and then we can take the individual ones and subtract it from the underlying risk to get the individual effect in the presence of only one exposure. So the REI would come about to be 0.08. So this is greater than 0. We would say there is evidence for positive additive interaction. However, we may have an interaction on a multiplicative scale. We can take the same example that we've taken in the earlier slide, where we would have the probability of a disease in the presence of a genetic and an environmental risk factor. How do we assess multiplicative interaction? First, we would calculate the risk ratios for each cell. So the risk ratio in the presence of both exposure, which is in the presence of environmental exposure and genetic risk factor, would be this one. We can take the P11, divide that by the underlying risk, and we would get the risk ratio for that cell. And then we can do the same for the individual exposures. So the risk ratio for environmental risk factor would be R001, and then the risk ratio for the genetic risk factor would be RR10. All we are doing is taking the individual cells, the probability of a disease, dividing it by the underlying risk, or in the absence of both exposures, which is P sub 00. So on a multiplicative scale, we would take the ratio of the joint exposure when E is equal to 1 and G is equal to 1, divide that by the cross product of the presence of individual risk factors. And we would take that value and look at the number. In this case, instead of taking 0, which was on a risk difference scale, we would take 1 as our reference value. If it's greater than 1, there's an evidence of positive multiplicative interaction. If it's 1, there is no evidence of multiplicative interaction. And if it's less than 1, we would say evidence of negative multiplicative interaction. Let's look at this in the same example that we have seen earlier. Before we see that in an example, let's look at this in a case control study, where instead of a risk ratio, if we have an odds ratio, we would do the same thing. It's not different from what we have done earlier, except we have to calculate odds instead of risk ratios. So as you might recall, the way we calculate odds is we take the odds for a specific cell. So the odds of a disease in the presence of both exposures would be, we would take P11 over 1 minus P11. We would divide that with the underlying odds in the absence of both exposures, which would be P00 over 1 minus P00. We would do the same thing for the environmental one as well as for the genetic risk factor and calculate the odds ratio for the specific cells. And if we take the ratio of odds ratio for the presence of both exposure, environmental exposures, as well as the genetic risk factor, and then divide that by the individual exposures, then we would get the same scale, multiplicative scale, and the interpretation would be similar to what we have done in the earlier slide. If it's greater than 1, we would say there is evidence of multiplicative interaction. If it's 1, we would say there is no evidence of multiplicative interaction, and less than 1 would be negative multiplicative interaction. If we look at this using an example, a similar example that we have seen earlier, we can try to evaluate if there is an evidence of multiplicative interaction by calculating the risk ratio. Because it's a cohort study, we would take the joint exposure where we have 0.015, divide that by 0.02, we would get the risk ratio for the cell. We would do the same for the environmental and genetic risk factor and calculate the risk ratios for each cell. And we would get 7.5 for the joint, 2.0 for the presence of genetic risk factor, and 2.5 for the presence of environmental risk factor. So we would take the 7.5 value divided by the product of 2 and 2.5, and we would get 1.5, which is indicative of an evidence of multiplicative interaction. So we would say there is positive multiplicative interaction. Similarly, we can do the same for a case control study. As we said earlier, in case control studies, we have to calculate the odds of a disease in each specific cell. So the first one would be to take the joint exposure, so 0.15, we would calculate the odds in the presence of both an environmental as well as genetic risk factor. 0.15 divided by 1 over 1 minus 0.15, and then we would divide that by the underlying odds in the absence of both the environmental as well as genetic risk factor. If we do the math, we would get 8.65 for the presence of both an environmental as well as genetic risk factor. And then for the individual ones, we would get 2.04 and 2.58. We would do the same as we have done it earlier. We would divide the odds in the presence of genetic as well as environmental risk factor and take the cross product of the presence of each factor, and we would get 1.64. This would be an evidence of a positive multiplicative interaction. Lastly, this is something that we oftentimes see in the published literature, and this might be something that you are mostly familiar about, which is assessing interactions in a regression model. We can assess interaction in regression models using both scales. There could be an additive interaction or a multiplicative interaction. Oftentimes, in a published literature, you would see multiplicative interaction. Additive interaction is not something that is commonly reported, but I highly encourage you to do so. So if we look at a linear regression model where we have the probability of a disease in the presence of a genetic risk factor when G is equal to G and the environmental risk factor, we would write this as alpha, which is the intercept, and then the genetic risk factor, the environmental risk factor, in the presence of both. So we would write our model this way, and we would get our probability of a disease denoted as alpha 0 would be P00, which is the underlying risk in the absence of both an environmental as well as the genetic risk factor. And you can know this if you substitute all the G and the E values by 0, you would get the underlying risk. So in the absence of either of risk factors would be P00. And then alpha 1, which tells you the risk for a genetic risk factor, would be P10 minus P00. And we would do the same for alpha 2. And then we can get our alpha 3 RERI, which is interaction on additive scale. So this is something that one can do in a linear regression model. This is not something most frequently done, but encouraged in epidemiologic studies. On a multiplicative scale, this is something that we can do in a log linear model or in a binary logistic regression model, where we would have the log of a disease in the presence of a genetic as well as environmental risk factor could be described as beta coefficients depicted here, where we would have the underlying risk, which is beta 0, the coefficient, and then we have beta 1 indicating was the genetic risk factor, and beta 2 for the environmental risk factor. and beta 3 for the interaction or in the presence of both risk factors. We would describe the interaction on a multiplicative scale similar to what we have done earlier, which is RR11 in the presence of both exposures divided by the presence of each of the exposure, which can be calculated using the exponential function of the regression coefficient for each of the variables. We can also calculate additive interaction from a regression model on a log linear model or on a binary logistic model. Earlier, we saw how we can calculate that in a linear regression model. What if you have a logistic regression model? You can follow the same format and be able to calculate the additive interaction when we use multiple logistic regression or log linear model. And this is something that will be covered in biostatistics lecture. But briefly, what we are saying is the RERI could be calculated as the joint subtracted by the individual plus 1. And this is consistent with what we have done for the linear model. What if we have a case control study? It's the same thing. It's nothing different than what we have done earlier. We would take the ratio of the odds for the presence of both exposures divided by the presence of either of the exposure. So this is an interaction on a multiplicative scale when we have case control studies. This is something that we used in many studies. Many of the psychiatric epidemiologic studies tend to be case control studies where we use logistic regression model. So this might be something that you oftentimes used in your studies. Just as a final words of guidance, additive versus multiplicative interaction, when should we use them? For some time, if you look at the epidemiologic literature, there was a debate whether which scale one should use, whether multiplicative interaction or additive interaction. And the general consensus was often the additive scale is of interest to public health importance. It would allow one to see whether the effect is different in subgroups, and that might allow you to maximize the public health benefits. The additive scale is also seemed to correspond to more the biological notion of synergism as described by Ken Rothman in 1976. So when we are thinking about biological interaction, the additive scale seems to correspond more to that notion. However, sometimes multiplicative scale may be better, or neither scale may be better, one that naturally corresponds to biological mechanism. So one has to base their decision on the biological understanding of the etiology that you're trying to study, but also what is the important matrix for assessing public health impact is something that you try to ask. If you look at in most published studies, as I said, interaction are evaluated and reported in multiplicative scale. That is probably what most of you are familiar with. But interaction on the additive scale is often not reported. There was a published literature about 11 years ago that showed 1 in 50 epidemiologic studies reported interaction on the additive scale. So the focus on multiplicative interaction, as I said, might be because of its ease in using statistical models, which are commonly applied, for example, in logistic regression analysis, and the fact that the models are immediately provide interpretation or interaction in multiplicative scale, and people tend to use them without necessarily thinking which scale the interaction is. But in general, our advice is from epidemiology point of view, if interactions are interest, it's probably good to report them on both additive as well as multiplicative, and also to calculate confidence intervals. One caveat is statistical interaction is not necessarily biological interaction. So that's something that we have to pay attention. So several investigators have pointed out the potential danger of using statistical interaction to draw conclusions about the biology. It has to be the other way around. It has to be driven by a question from biological understanding of a disease etiology. We try to assess confound effect measure modification. It's the same even with confounding. We try to base our knowledge not in a data-driven statistical analysis approach, but we try to base it based on prior knowledge, looking at the literature. How to conceive of biological interaction is still an active area of research. There are several investigators who are continuing to refine our methodologies, and additional assumptions are needed to infer biological interaction, not just based on statistical understanding. So if we just look at this example that was published by one of our colleagues, a faculty member at Boston University, Jamie Gradis, where this study examined the association between post-traumatic stress disorder and completed suicide in a population-based study in Denmark. So the investigators evaluated interaction, as you can see, using RERI reported here by calculating the relative risk due to interaction, which is a departure from the additive effect. So a departure from the additive effect is what they have done. But they haven't calculated multiplicative interaction, and we can easily calculate multiplicative interaction as we have done it earlier, which is taking the odds ratio for the presence of joint exposure, 29 provided here, and then the multiplication of the individual odds ratio, which gives us 0.36, which is less than 1. The investigators reported there was an evidence on interaction at an additive scale, but as one can see by calculating those values, we can see that there is no evidence of multiplicative interaction. Another final example to just give you a genetic epidemiology focus in this study, which was conducted by investigators from the Psychiatric Genomics Consortium, where the genetic effects of major depression disorder are evaluated using PRS, which will be covered in our session's polygenic risk scores. In particular, the investigators tested if there is interaction by history of childhood trauma, and childhood trauma was evaluated in different stages. And what they have done is this interaction in epidemiology is oftentimes important because they're trying to understand the effects of the environment on etiology, on a disease, on depression, but how that is interacting with another exposure. So this is something that we oftentimes call gene-environment interaction. So gene-environment interaction is something that is oftentimes useful and highly encouraged in our epidemiologic studies. That concludes our session in interaction and effect measure modification. It was a quick overview. I hope you find it useful. Look forward to seeing you in the class and be able to discuss those in greater detail as we go through our lab analysis.